Hello, hello. This week's Fiddler I thought was very, very interesting. Very fun puzzle to solve. It's got a lot of geometry, which I really enjoyed. I found out I'm a bit rustier than I thought I was at doing this kind of thing, but it was really enjoyable to kind of bring those tools back out. And it was also really fun. I got to work on this with friend of the channel, Abdul the Killer, a lot. And they kind of really carried me through a lot of this, and they provided some of the visuals. So big, big thanks to him for that. Anyway, so what is the problem this week? It is a cake splitting problem. So we've got a cake. It happens to be a rectangle. We want to divide the cake among three people fairly. And fairly in this context means that there are two conditions on how to be considered fair. The first is that everybody gets the same size slice of cake. And for the purposes of this problem, it really doesn't matter what the height of the cake is, like from the bottom of the cake to the top of the cake. And we're effectively going to treat this as a two-dimensional cake. If you add height, you can add that dimension and multiply everything by that height, but it's not going to change any of the fundamental features of the problem. So we're going to ignore it. So we're going to pretend it has height 0, and I'm going to talk about the area of the cake, then that being essentially the size of the slice, and the perimeter of the cake. So the other thing that has to be about that to make the other thing that will make this fair is that for some reason, this is not me, but for some reason, everyone likes the icing on this cake. And they want an equal share in the icing. And since the perimeter of the cake has more icing than the rest, they want to equally split the perimeter of the cake. So those are the two conditions that would make a slicing fair. And here they have two pictures of how you might do this for a circle and a square. It actually is interesting. I thought that maybe with the square case, there was only one possible, or four possible orientations for how that would look. But it turns out that if you equally split the perimeter and go exactly to the center of the square, the areas are going to be equal no matter what. And there's a cool little geometric proof that I'll leave to you to find or do yourself. Hopefully, by the time we figure out how to do this with rectangles, the square will be easy. But it is an interesting little result there with the square as well. But here we're going to do a rectangle. So how do we do this? So we have a rectangle. The ratio of the dimensions is going to be pretty important here. And in this particular case, we've got a length of 20 and a height of 10 on this rectangle. And my first step is going to be just what's the total perimeter? It's 60, right? Add up the length of the sides. And the next step is to say, well, then what is the length of perimeter that each person is going to get? Well, because the perimeter has to be divided equally. So if there's 60 total perimeter to divide among three people, that means everyone has to get 20, right? Okay, so far, so good. Now my question is going to be, well, where are those 20 points, where are those perimeter points going to be, separated by a length of 20 on this rectangle? And there's no reason to think that they couldn't go anywhere. And it turns out they can go anywhere. I mean, as long as they're equidistant from each other, right? As long as the perimeter distance between the points is 20 for all points, then you can put them anywhere. It wasn't obvious to me that that was true. I thought there might be some places where it would work and some places where it might not work. But it turns out you can put them anywhere. But for the purposes of finding just a solution to this problem, which is the first step here, I'm going to choose a particular point, which I thought was pretty conspicuous, which was to have two of the kind of division points between the slices be on corners, right? So if 20 is the perimeter and also 20 happens to be one of the lengths of the sides, that shouted out to me, hey, that should probably be one of the perimeter slices. One of the slices of the perimeter should be those length of the side. And you could, everything's going to be exactly symmetric if I do this with the top corners or the bottom corners. I chose to do this with the bottom corners. It doesn't really matter. And so we're gonna explore what that might look like. So if I put little dots here representing the perimeter points of my slices of cake, then I can connect them with a triangle, and that's going to help me figure out where the center is going to be, right? Because I don't know where the center point is going to be. At some point, I have to pick one center point in this rectangle, and from that center point, connect to all the perimeter points. And that will divide the rectangle into three shapes of some kind. And hopefully, the areas of those slices of those shapes will be equal. And my first thinking here was to connect these perimeter points and figure out what the areas outside of that are. And so the reason that's relevant is if the area, I mean, it certainly is going to be true to me fairly obviously that the area of these triangles outside the big triangle are not going to be big enough to satisfy a slice. And so if you look at the area of those outer triangles, they are going to be 50, right? And because the areas are 50, that is not a third of the cake, right? The area of the entire cake is 200, so everyone should be getting 200 thirds, which is 66 and 2/3. So that's more than 50. So we're going to need more than that. And the reason that these triangles are important is there's no way, because I only have one central point to pick from, I kind of have two choices. I can pick a center point inside the purple triangle, and if I do that, that's going to add essentially another triangle to the green and red slices. Or I could pick a point in the green or red triangles, but if I do that, that's going to take some of the slice away from one of those triangles, and that's going to make them too small. So I know the center point is going to be somewhere in this big purple triangle because both the green and red triangles need to grow in order to have them equal 1/3 of the area of the entire rectangle. So at some point, I'm going to pick another. I'm going to pick another point here in this purple triangle somewhere. That's going to make 3 triangles, right? Effectively, it's going to make another triangle that adds to the green slice, another triangle that adds to the red slice, and whatever's left over is going to be its own triangle. And I'm actually not going to think about the green and red triangles right now. I'm going to think about the new triangle that gets formed. So if I pick another point anywhere in the center, that's going to form a triangle with these 2 bottom points, right? And I think about how much more it needs, then this new slice is going to have to end up with an area of 200 thirds, right? 200 thirds is going to be the area that I need for this slice. So how do I do that? How do I make sure the area has 200 thirds? Well, it turns out all I need to know is the height of that triangle, right? So if I think about the formula for the area of a triangle, right, it's 1/2 base times height. I know the base, right? The base is going to be 20. And then I'm going to pick a point somewhere up here. It's going to be some distance away from that bottom of the rectangle. That's going to be the height. And that's going to define the area no matter where it is kind of in x coordinates. So since this new slice that I make is going to have a base of 20, what's the height going to be? Well, I can just rearrange this area formula and figure out that the height is going to be 20 thirds. That's going to be the height of this triangle. So, but then the question is, well, where is it going to be in x space? And, for the purpose of this problem, I'm just going to appeal to symmetry here and say there's no way that I can make this point more to the left than the center or more to the right than the center, because the red and green triangles would then be asymmetric here and have different areas. Now, if that's not obvious to you, I will, when we go into the extra credit, we'll talk about ways to do this a bit more rigorously. Therefore, you'll be able to do this on your own for the individual problem. But for now, before we get into the extra credit, I'm just going to appeal to symmetry and say, look, then the new point I draw is going to have to be 20 thirds from the bottom, exactly centered in the rectangle. That's going to evenly divide the rectangle into 3 slices that each have equal area and equal cake perimeter, right? Not perimeters of the individual shapes, but the cake perimeter. So that's the original problem. And now I'm going to switch gears and talk about the extra credit for a bit. Okay, so here I have this nifty diagram showing what the rectangle is going to look like when it's all sliced up. You can see there are areas here indicating how big each slice is, and they're all 200 thirds roughly. Now I'm manually dragging these points around, so it's not exact, but this is roughly what that cake's going to look like when I split it up. Now the extra credit asks, well, so this is one solution to the original problem, but there's not just one solution. In fact, there's an infinite number of solutions, and all of the solutions end up having a different center point. So unlike the square, where all the ways to divide the cake end up with the same center point, here that point's actually going to move around a bit. And the question asks, what's the area of the shape created by all of those points, where the points are the perimeter of that shape. So we have this neat little tool here which says, well, what happens if, so I did this for the endpoints being exactly in the corners and then 1 point in the central top. Now, what happens if I just kind of move these a little bit? So these are going to drag with each other so that if I move the bottom left corner a bit to the right, it's going to shift the other perimeter points to maintain an equal perimeter here. And what you can see is that the area of these triangles is changing, right? So that center point is not going to work for all of these individual possible solutions I could make. So how do I find, like, suppose I just pick a random, I move some distance, these perimeter points some distance here. How am I going to shift this around, right? Where do I put my center point to get um, exactly at the point where the slices are all equal? And there is such a point, right? For any perimeter point I choose, there is such a point, but how do I find it? And the logic is going to be fairly similar, right? So I can think about now these slices here, right? The kind of the outside the triangle slices, right? So wherever I put the center point, I mean, I guess I could put it out here, but if I put it outside this triangle, because one of them is definitely going to be too small because these outer slices are always going to be less than 200 thirds. So I've got to be in this triangle somewhere. And where I need to be is going to depend on exactly where I put my perimeter points. But if I just pick this point, like for a given set of perimeter points, how do I solve where the center point should be? And it turns out there is a neat construction that you can do, which is just like before, I can think about these outer shapes as having a known area, right? If I know all these perimeter points, I can calculate the area of each of these triangles, right? So if I call this distance z, right, the distance between the corner and my perimeter point P, then here I've got a trapezoid. It's got a height of 10. It's got a length here of z. And then up here, I will have effectively 10 minus z because, you know, if I go here, right, r is exactly halfway. So this length originally is 10. And if I move P to the right Z, R is going to move to the left Z. So my top has distance 10 minus Z. So the average of 10 minus Z and Z is 5, right? So you can think of the average of these trapezoid lengths is 5. It's got a height of 10. And so this area is actually always going to be 50. The area of this trapezoid is always going to be 50, no matter where I put this P. Actually, if I get all the way to here, no, that still works. Yeah, it's 10 and 10. Yeah, that's still 50. So even when it becomes a triangle all the way to this corner, it's still this triangle now. It's a triangle instead of a trapezoid, but it still has area 50. Anyway, so this red, mostly trapezoid, is always going to have area 50. But the area of the green and blue triangles here are going to change as I move this, right? So again, if this is Z, this blue is 20 minus Z, this height is also Z, and so the area of this blue triangle is going to be, you know, 20 minus Z times Z over 2, right? And I can do the same thing with the green, and of course that depends on Z. I can do the same thing with green, that's also going to depend on Z. And it doesn't matter what the exact formula is for now. All that matters is that I can figure out what that area is just as a function of this distance, right? This distance that I've moved the perimeter points. So I know the area of all of these three shapes. And so what that means is now I can figure out, okay, well, what does the size, if I think about these three triangles being added to that, what do the areas of those triangles need to be? Right? That is the fundamental question. That's kind of the important observation here, is that I can answer, if I know the heights of these triangles, that's going to somehow lead me to the center point. So how's it going to do that? Well, again, so if I know that this red trapezoid has an area of 50, that means I need this red triangle to have an area of 200 thirds minus that, right, which is 50 thirds. So how do I make this area 50 thirds? Well, again, I know the base of this triangle, right? I know the base of this triangle, and the base of this triangle, the trapezoid one's actually kind of hard to see because I need to, right, kind of divide this into a rectangle and another triangle. And if I do that, right, I'll end up with, you know, a height of 10, and then this is going to end up being 10 minus 2z, right? Because if the length of the trapezoid is 10 minus z, I've got a z of rectangle here, so what's left is 10 minus 2z. So I've got the side lengths of this triangle, the hypotenuse. I can use the Pythagorean theorem, right? It's going to be the square root of 100 plus 10 minus 2z squared, the square root of all that. So that's gonna be the hypotenuse of this triangle. Again, it's all in terms of z. So if I just know this distance, which again I'm calling z, I know the area of each of these outer shapes, and I know the length of this triangle, right? And all sides. So I know the base of this triangle. I know the area I need, which means I know the height of this triangle, the perpendicular height of this triangle. And that's going to create a line where if I put my center point anywhere on this line, and again, I'm manually dragging it, so it's not quite exact, but if I put it anywhere along this line, you can see that the area of the red triangle is about, 66 and 2/3. And it only differs because I'm dragging it across a thing with my hand and I don't have the manual dexterity to do it perfectly, right? So anywhere along this anywhere along this line, I'm going to end up with the correct area for the red slice. Now, hopefully you've then thought, well, I can do the exact same thing for the others, right? And if I do the same thing for the others, I get, if I have this parallel line, this line again is parallel to kind of this blue triangle line. And if I go anywhere along this line, the blue triangle now has the right area, right? And if I do the same thing with green, then with this parallel, the green slice is going to have the correct area, right? And so it's going to have to be true. The center point is going to have to be along kind of this green parallel line and this red parallel line and this blue parallel line, right? And of course, the only place that works is exactly in the center, right? So if I put it right in the middle here, I get about 66 and 2/3. And again, it's only about because I'm kind of manually putting it somewhere. It's about 66 and 2/3 for each of the slices. And so then you may wonder, well, how do I get this particular point? And I'll go into that in broader detail in a second, but I just want to make sure the intuition is clear that figuring out the shape of these, the fact that there are these parallel lines from this triangle where they all intersect, and further, if I move this, ignore the area, right? The area is not important, right? If I shift the shape around, meaning if I move the perimeter points, those three lines are always going to intersect somewhere, right? And you can kind of see it's making this kind of arc. The center is moving in a bit of an arc as I move this around. And in fact, let me show you a different diagram. So here you can see, again, our kind of original starting point. But now I'm going to kind of rotate through and have the perimeter points move around. And you can see that the center point shifts around and kind of makes this lemon looking shape, right? It kind of looks like this lemon here in the middle that kind of kinks when you get to the center of the rectangle. So this is what our locus of points is going to look like. And again, I will go through to figure out for a given set of perimeter points, how do you find the center point? And then finally, how we're going to find the area of this shape. So coming back to this picture, I'm rescaling the rectangle a bit. So I did all the math originally on a 2x1 rectangle rather than 20x10. I didn't want to redo it over to get all these equations again. So I just, I'm going to repeat what I did here. All the math is exactly the same. It's basically just scaled by 10. You can get some funky things when you have offsets, but basically when we get the area at the end, it's just going to be scaled by 10. Otherwise it's going to be exactly the same. I guess the area will be scaled by 100 because it's 10 in each dimension. Anyway, we know the area of each of these shapes that are kind of separated by this triangle, right? And we know them all in terms of z, which is the offset of these perimeter points from the bottom corners. And we can also figure out for each of these shapes kind of the length of that triangle using Pythagorean's theorem. And once we know that, we know the height that we need to go off of that to make a new triangle to add to that shape. In this case, we're going to get this equation. All this is going to eventually cancel out, so we don't need to worry too much about it, but I'm putting it here for now. So if you're trying to follow along step by step, you can check to make sure that you're right. And now what I'm actually more interested here is not the height, but the equation of this line, because eventually what I'm going to want to do, this is the line that is parallel to the kind of border between the red and purple shapes. So this line is important because eventually I can do the same thing with one of the other shapes. It doesn't matter whether I use blue or green, it turns out, because all three lines are intersecting the same point. If I can find out where this line intersects with the exact analogous shape, the exact analogous line from the blue triangle, that intersection point is going to be my cake center, the cutting center of the cake. And so if I can find the equation of these lines, I can find the coordinates of the intersection point. And so for this, I'm going to choose the center of the rectangle as the origin in term for all the kind of coordinate stuff I do. And that's how I'm going to do it. You could do it in another way, but it turns out that's just how I did it, and it worked out great. So so once I choose that, the thing I'm going to do first is actually get the equation of this line, right? The line that goes through the border between purple and red. And that line is fairly easy to get because I know the slope of it. The equation for the line is easy because I know the slope, right? I get that from these triangle shapes, and I can get the intercept because I know, I mean, I only need one point on the line, but I know two, right? I know where this line intersects the rectangle, right? I know the coordinates of those points. So I can get that intercept somewhat easily. But what took a little bit of geometry is figuring out, well, how do I then turn that into the equation of the line I care about? Because I need to know this vertical distance between them in order to do that. There are probably, more, there are probably better ways to do this if you are better at geometry than I am, but I'm quite rusty. So what I did is I extended this vertical line all the way up and notice that that makes two similar triangles, right? This little purple triangle in here is similar to this triangle here. Similar just means the angles of the triangles are all the same. And so everything's the same about them up to a scale factor. I know they're similar because they both are right triangles, right? The vertical line intersects a horizontal line, so that's a right angle. This height is coming off perpendicularly to, this line we care about, well, the line we care about, or the border line. So that's a right angle as well. And so those are the same. I also know that the angles kind of opposite two intersecting lines, which I'll call A in this example, are the same. So once you have two angles that are the same in a triangle, the third one will also have to be the same because the sum has to be 180 or pi, depending on if you're in degrees or radians. And I'm going to call those angles B. Those have to be the same. And I quite, easily know the angle B, right? So B is just going to be the arctangent of the opposite side of the triangle it's on, which is 1, over the adjacent side, which is 1 minus 2z. And then that gives me the vertical offset of this parallel line that left, above this 1 over 3 root, blah, blah, blah. That is the length of the hypotenuse of the triangle. And if I divide that by the cosine of b, which I'm leaving in terms of arctangents, then that will give me the vertical offset here. And you may be tempted to simplify this cosine times arctangent term, and that would be fine to do that here. But I actually waited and simplified at a later step, and I think that worked out quite nicely. I'm going to simplify this whole expression in a different way. So basically, if I come back to this picture, now I'm outlining this triangle, and I replace 1 minus z up here with 1 minus 2z because that's the length of this side of the triangle. What you'll hopefully notice is that this small triangle, this small red triangle, is also similar to the larger red triangle here, right? I guess I needed that to find the angle B. Now, once I know that, what that means is that the ratio between this hypotenuse, right, and 1 minus 2z here is going to be the same as the ratio of this height we know here and the thing we care about, right, because these are all similar triangles. And once you are armed with that, you can go back to your equations here, right, and say, well, my vertical offset is just, I'm going to call h that height, the known height we need of the kind of extra red triangle we're going to add there. And if you divide that by a cosine of b, or that angle, then that'll give me my vertical offset. But I also know, how did I get h, right? It was 2 times area over, I'm going to call this p now, where p is the base of the triangle, right? This a is the area of the red shape that we already have, 2/3 is what we want to get to. Um, if the area of the so we're now in the land where the rectangle's area is 2. So 2/3 is the total area I want. A is the area I know about. And so this difference is the area of the new triangle. So 2 times that area over the base of that triangle, which I'll call P, is the height. And so I can fill in some things here. So now h over cosine beta, all I'm doing is adding a cosine beta to the denominator of what I have here. But now P times cosine beta, right, by this same exact picture I have back here, right, P times cosine beta, again, P is the base of this big triangle, right? So P times cosine beta is just this side of the triangle, 1 minus 2z. So I can replace this with 1 minus 2z. I know the area of that shape is always a half. And so this whole thing is going to simplify quite nicely to 1 over 3 times 1 minus 2z. And so now I know I'm going to use this point here. And the reason I'm using this point is I'm going to eventually do the same thing with the blue triangle. And so I want to use the point that they have in common because it'll make doing everything else a little bit easier. Um, and so I know the coordinate of this point is z minus 1, or I think of that as minus 1 plus z, right? So this point here is minus 1 in the x dimension. So if I add z to that, that'll give me the x dimension here. And since the origin is the center of the rectangle, the y coordinate of the bottom is negative a half because the whole length is 1. So I have this coordinate point here. I know the slope of this, right? It's just, 1 minus 2z is the x distance this travels along this triangle, and 1 is the y distance that this travels. And so if I plug that into this equation, I'll know that y, the coordinate point I have, negative a half, is the slope times the x point I know plus some unknown intercept. Rearrange that a little bit, and I get an intercept here. The equation of the line I care about is basically y is the same slope because it's parallel. And then here I've got this exact same term I have b from what I just calculated minus that vertical offset that we just simplified. And it turns out that this will simplify a bit too. And this gives us a nice equation of this line. I'm not going to go through each individual step, but you can go through the exact same process for the blue triangle and find the equation of the line that gets offset there. It turns out to be this. And if I want to find the point of intersection, right, that x coordinate is going to be the difference in the intercepts divided by the difference in the slopes. And it's important that these are in different directions. And that also will simplify somewhat nicely in terms of z. Do the same thing for y, which is going to be, slope times the x coordinate I just found plus b plus the y-intercept of those lines. That will all, and it doesn't matter which one you choose, you'll get the same answer, and that will also simplify somewhat nicely. And if I start with these points now, well, so what am I going to do with this? What's the point here? Well, it turns out that if I have these x and these y points in terms of z, and I don't have a good, this is the point in my solution that I'm not quite satisfied with my method here, which is I know, I mean, I can kind of intuit that these points in terms of z are going to form an ellipse. So I know, I think they're going to form an ellipse, and I can check that that's true, and I can kind of guess the equation of the ellipse and verify that that's true. But I don't have a good proof of why this has to be an ellipse, right? So the best I can kind of do here is make a guess, right? So I'm going to guess that the ellipse equation looks like this. And so where does this guess come from? Basically, this guess comes from the fact that, well, I know there's going to be a difference in the scaling of root 3 because of, or I'm going to guess at least, that there's a scaling of the root 3 because of this 2 in the 6th term. I think that's where those root 3s are coming from. The 1/2 is kind of coming from this 1 minus 2z, I think. But basically, I'm kind of just guessing and checking here until I found something here that ended up with an ellipse. But regardless, this does work. So if you plug in this z term right here for x in this equation and this z term here for y, then you will end up all of those z terms end up canceling out, and you'll just get a 1. So this equation is correct. This is the equation of the ellipse or at least one of the ellipses that I care about. Right, but going back to this image, what you hopefully are recognizing here is that I don't actually have an ellipse, right? This shape is not an ellipse. What I actually have is the intersection of two ellipses, right? So when this point kind of crosses these corners, I'm changing from one ellipse to another. And so what I'm going to do, what I essentially need to do is find the area of half of this ellipse, right? So if I think about breaking this in half, so what I've actually found is kind of the ellipse equation that I just showed you is for this left half of the shape. And so what I'm going to do is find kind of half of this area, and then I'll just double it to find the whole thing because it's perfectly symmetric. How am I going to get the area of this segment? Well, basically, I'm going to take that, pretend this is an ellipse, stretch it into the unit circle, and then figure out this area in the circle, and then stretch it back. So finding the area in the circle is the easy part of this. If I know this angle A, which again, we'll have to figure out what that angle is, but if I know this angle A, the area is just going to be capital A area is going to be this lowercase a angle minus sine of the angle all divided by 2. So where does that formula come from? Basically, A over 2, A being the angle, is this entire wedge in the gray triangle and the purple segment, right? So basically, if this is a unit circle with radius 1, the area of it is pi, because r is 1, so pi r squared is just still pi. And the entire angle has a radius of 2 pi. A as a fraction of that would be a over 2 pi. And so a over 2 pi times the entire possible circle angle, 2 pi, would be, a over 2 pi times pi is just a over 2. So that's the area of this wedge. Whereas the area of this triangle, there's a somewhat, it's not as well known as 1/2 base times height, but there's another area for the form of a triangle, which is 1/2 times the length of two adjacent sides times sine of the angle between them. Basically, you can think of the angle between them times sine of sine of the angle between them times one of the lengths as the height in the base of this triangle. So it really is the same formula, just rearranged with a little bit of trigonometry. And so that's sine a over 2. That's where that comes from. We're subtracting out the area of this triangle. Okay, so how do we stretch this out? So let's think about the ellipse we have, and I can kind of put it I can put some points on it based on what we know from the equation of the ellipse. So I know that from the equation of the ellipse, I know the center of it is going to be at 1/2, 0. And I know the top and bottom of these segment points. So how do I know those? Well, I know those from the solutions we kind of already done. So I know that the top of that shape is going to correspond right here. I know the top of the area I'm looking for is going to correspond to the solution in which the bottom corners of the rectangle are perimeter points, and so is the top of the middle of the rectangle. We did that, right? We found 20 thirds, but if we scale it down, that would be 2 thirds. 2 thirds up from negative 1/2 is going to be 1/6. So we're going to be at 0, 1/6 for that point. If I flip the whole thing 180 degrees, I'll be at 0, negative 1/6. So those are those points here. So I know the length of this chord here is going to be 1/3. I also know the stretch factors of this ellipse, right? Because there's a 3x in the equation here without any other constants on x, then I know that 1/3 is essentially the distance of the ellipse from the center to the left edge. And since 3√3 is the y stretch factor, I know that 1 over 3√3 is going to be the length of the ellipse here. And so when I translate this into the circle, basically I'm going to take this ellipse, I'm going to multiply all of the widths by all the x dimensions by 3 and all of the vertical dimensions by 3√3. I'm going to get rid of the coordinates because they're not really important anymore. And I'm just going to take that distance that used to be 1/3, multiply that by 3√3, so now it's the square root of 3, and I'm on the unit circle, so these radiuses are going to be 1. That's really all I need to do this. And so from these, I can then get the angle of the center using the law of cosines, right? So for any side C, remember, if you take away this the cosine term over here, this is just Pythagorean theorem, right? C squared is a squared plus b squared. So that works here too. So if C is a right, capital C is a right angle, capital C being the angle across from side C. So in this picture, this vertical line is going to be side C, and this angle is going to be capital C. But that's a right angle. The cosine is 0, and that's just going to cancel out. But here, it's not necessarily 0. So filling that in, right, root 3 becomes 3. In this equation, these other sides have length 1. And solving this for cosine C is just the arc cosine of minus a half, which is 2 pi thirds. So I can plug that back into our area equation, and we can simplify a little bit to get pi thirds over root 3 over 4. So that's the area of this on the circle. I then need to do a couple things to get my final answer, right? So to get the ellipse area, I'm going to restretch that by the same third and 1 over 3 root 3. This time, I'm going to be decreasing everything by those, so that should get smaller, right? And then I'm going to double it to double that segment, because remember, the thing we're looking for is that kind of flipped of the segment we just found, plus it flipped horizontally. And then I'm going to multiply by 100 to go back to our original rectangle. So if I do all that, right, I take this area that I found before times 200 and divide it by 9 root 3. That's just 3 and 3 root 3 together. And so I get something like 200 times, this this business, which is about 7.88. And that's where I get. So hopefully you learned something. If you have any questions about any particular step that I glossed over too fast, feel free to leave in the comments, and I'll try to help. All right. Thanks everyone for watching. I'll see you next week. Bye.